Hey guys, Mr. Betts here. I want to talk about another way that we can use to show that a series converges or diverges, and that's going to be with the integral test. And so, what we're going to do here is we're going to use an improper integral to show that a particular series is going to either converge or diverge. So, I want to look at a geometric example. On the coordinate plane, if we look at the area of the rectangles here, notice that we have a function graphed. F of x is 1 over x. So the height of each rectangle we can get using that function by plugging in the x value. And so the height of this is going to be f of 1, which is 1. The width of each of these rectangles is going to be 1 because it's just going between the integer values here. So the area of each rectangle is pretty easy to compute. And so the areas are going to be 1, 1/2, 1/3, 1/4, 1/5, and so on. So the total area of the rectangles then will be what we get when we add all of these together. This series should look a little bit familiar to you by this point. It's actually the harmonic series. And so the question is, what is the total area of the rectangles? And to answer that, we are essentially looking for the sum of the harmonic series. This, like I said, is a series that we should be a little bit familiar with, and this is a divergent series. So this series actually goes to infinity. I want to convince you that that series goes to infinity in another way than we've talked about before. So let's take a look. Instead of the area of those rectangles, let's look at an area that can be represented by an integral. So the red region right here would be represented by an integral that would be the integral from 1 to, this is going to go to infinity. We're going to look at what happens as this goes to infinity of the function 1 over x with respect to x. So this integral right here is an improper integral, but it's an integral that we can evaluate using a limit. So if we replace that infinity as the upper limit with some constant and look at this integral right here, and then look at what that does as c approaches infinity, we can evaluate that. And it turns out that that does approach infinity. That is an infinite sum. So one more thing that we want to look at then is, how does the area of those rectangles compare to the area that is shaded in red? So more specifically, how does the area given by this integral compare to the area given by the harmonic series? And so I think it's pretty clear, but I just want to point this out, that on each subinterval, the area of the rectangle is just a little bit bigger than the area under the curve. And that over approximation, that area that's a little bit too big, is getting smaller and smaller, but it's still always going to be an over approximation. So it turns out that the area given by the rectangles, which is the harmonic series, is bigger than that integral. Well, this integral, if we were to evaluate it using a limit, because that's how we evaluate improper integrals, turns out that this integral diverges because the limit approaches infinity. Well, if this is growing infinitely big and this is bigger, then that harmonic series should also diverge. So what we're doing here is we're using an integral to approximate an area. In this case, we're using LRAM on a decreasing function, and we know that left rectangles are going to be an over approximation on a decreasing function. And since that left approximation is an infinite sum or an infinite area, then we know that the sum that it approximates is going to be infinitely big also, because it's going to be bigger. So this idea gives us what's called the integral test for convergence. And it's a little bit more powerful than what I just talked about there. There's a little bit more to it than that. But essentially what it says is, if there's a function that matches a series term for term, and we can evaluate the improper integral of that function, then the sum that that function approximates, if that sum converges, then the the improper integral converges. If the improper integral diverges, then the sum diverges. So they're both going to do the same thing. So the sum and the integral are both going to converge, or they're both going to diverge. So the integral test for convergence is very powerful if, and this is very important, if we can approximate or match up term for term the series with some function. And not only if we can match it up term for term with some function, but also if we can actually evaluate the improper integral of that function. So if we're able to do that, and that function does have to meet a few criteria here. It has to be continuous, it has to be positive, and it has to be decreasing. So I mentioned the decreasing part when we looked at this example here at this picture. But if it meets all of those criteria, then if the integral converges, then the sum converges. If the integral diverges, then the sum diverges. So in very specific situations where we know what the improper integral of some function is, or if we're able to evaluate that, then we can determine whether the series that matches up that function is going to converge or diverge also.